Hello everyone. Today we will be talking about the common-emitter amplifier circuit. First, we will provide an overview of the common-emitter circuit, specifically the low-frequency model, continue on by going over one of the common introductory bias circuits for the common-emitter, then moving on to the small signal model, and concluding with a lab demonstration of the circuit. The common-emitter circuit is a simple single transistor circuit that provides voltage gain. Many circuits use it as an amplifying core, as it is the simplest transistor circuit that provides amplification. Inside many bipolar op-amps, it is used as a gain stage, and a variant of it that uses two transistors, called a differential pair, is used in the input stage of bipolar op-amps. It is also used in high-frequency RF amplifiers, where the simplicity of a single transistor amplifier translates into lower parasitic capacitance and inductance, which are important for high bandwidth applications. Most bipolar circuits that perform voltage gain have some form of common emitter circuit inside them, though there are many variants that we will not discuss today. Today, we'll only talk about its basic form. Here we have a schematic of the basic form for a common emitter circuit. We have an input voltage on the base with a source resistance, and a resistor from the collector to a power rail with the output taken off the collector. However, in order to properly bias this circuit, we're going to add a few more components. So we've added two biasing resistors, an AC coupling capacitor on the input, an AC coupling capacitor on the output, and an emitter resistor with a bypass capacitor across it. It's called a bypass capacitor because the AC current travels around the resistor through the capacitor instead, effectively bypassing the resistor. This is a similar setup as we had in the previous episode. This allows us to more easily control the collector current and not have to do an awkward DC offset shift on the input, so long as our amplifier doesn't need to amplify all the way down to DC. So let's start by converting this to the biasing circuit at DC by opening up the capacitors. Recognizing that we can use the equation from the previous episode, we have the resistive divider equation on VCC along with the correction factor for base current that gives us our base voltage. However, we're going to assume that the biasing resistors are large enough, our beta value high enough, and our required collector current precision low enough that we can ignore the correction factor due to base current. Using the general assumption that the base emitter voltage is about 0.7 volts, and assuming we're in the forward active region, which we'll verify in a moment, we can use the base voltage to determine the emitter current. And continuing with our assumption of high beta, we assume collector current and emitter current are approximately the same. So we can get the collector current out of the transistor with this equation, which is the main parameter for our small signal model. Now back to ensuring we're in the forward active region. In order to do that, we need to ensure that our circuit setup keeps the collector voltage above the base voltage and the base voltage above the emitter voltage. So the collector voltage is given by VCC minus this VRC voltage drop across the collector resistor, which is equal to IC times RC. VE is equal to this voltage drop VRE, which is equal to IE times RE, though we continue with our approximation that beta is high, so it's approximately equal to IC times RE. Recalling that the base voltage is approximately equal to VE plus 0.7 volts, which satisfies the VB greater than VE condition, that leaves us with VC must be greater than VE plus 0.7 volts. Plugging in our approximate expression for VE, we have VC is greater than ICRE plus 0.7 volts. Plugging in our expression for VC in terms of IC, we get VCC minus ICRC is greater than ICRE plus 0.7 volts. Simplifying this equation and solving for IC, we get that IC must be less than VCC minus 0.7 volts divided by the series combination of RE and RC. So long as this equation is satisfied and the collector current is not set too low, then the transistor will remain in the forward active region. I've put this equation in terms of IC rather than the parameters above in our IC equation because a target IC is usually decided upon when beginning or iterating on an amplifier design, and so you generally design the components around a target value for IC, so it is usually easier to think about subsequent parameters in terms of IC. So now that we have our collector current, and have ensured the transistor is biased into the forward active region, we can move on to the small signal circuit, which is the more interesting portion of the common emitter circuit. Looking back at our complete common emitter circuit, let's convert this to the small signal AC version. So here we've shorted the 3 capacitors and converted the static DC voltages to grounds. It looks very similar to the ideal common emitter circuit we showed early on in the video. The only differences are that this is the AC model, so the rail voltage is ground, and that there's an additional resistor on the base that consists of the parallel combination of RB1 and RB2. So, using the small signal parameters we derived in the previous video, here is the circuit converted to its small signal equivalent circuit. We note that in this configuration, due to the grounded emitter, RO and RC are in parallel, and the 2 biasing resistors and Rpi are also in parallel. RC and RO being in parallel can be a little disorienting, but it's only because the emitter is grounded and because the rail is a static voltage, making it equivalent to an AC ground. So, cleaning up the schematic, we get this circuit, with this new resistance RB', defined as the parallel combination of RB1, RB2, and Rpi. With a single-ended input and single-ended output voltage amplifier, the 3 main parameters of note we'll want to derive are the gain, input impedance, and output impedance. Let's start with the gain. To get that, we need to find an expression for Vout in terms of Vin and known parameters or constants. Now we can see that Vout is the voltage drop across the parallel combination of RC and RO, which is given by negative RC parallel RO times IC. And we know that IC is equal to GM times VBE per the model, and we note that VBE equals VB since the emitter is grounded. So all we need to do now is find VBE in terms of Vin and known parameters. Looking at the input side of the circuit, we see that the source resistance, Rs, makes a resistive divider with the composite resistance Rb', and since the VBE voltage is the voltage drop of the bottom resistance, we can simply apply the voltage divider equation to get VBE equal to Vin times Rb' divided by Rb' plus Rs. Let's expand out Rb' to display the hidden variables. So now we have VBE in terms of Vin and Vout in terms of VBE. We just substitute the expression we just wrote in for VBE in the Vout equation, and get the following equation. Gain is defined as Vout over Vin, denoted by lowercase av, due to this being a small signal gain, which results in this expression for the gain. We'll go over the implications of this gain expression once we've derived the input and output impedance. Moving on to the input impedance, which is measured to the right of Rs, as Rs is part of the input circuit and not the amplifier circuit, we can see that the input impedance is very trivially Rpi in parallel with Rb1 and Rb2. Finally, we'll take a look at the output impedance. Here it might look a little more complicated than with the input, but we can make the simplifying observation that the small signal collector voltage has no impact on the current through the current source. And so you can see that the output impedance is the output resistance Rc in parallel with Ro. To make it clearer though, let's extract it more formally by using a test current. If we put a small test current load, Ix, on the output, since IC does not change because VBE is unaffected, then all that test current flows through the parallel combination of RC and RO and into ground. We can use this test load current in 2 cases. In the first case, we shut the test current off, and Vout for this case, which we'll call Vout1, is equal to negative IC times RC in parallel with RO from our previous equation. In the second case, we'll turn the test current on, and Vout, which we'll call Vout2 in this case, is equal to negative IC minus Ix times RC in parallel with RO. In order to get the output impedance of a linear AC circuit, we just need to measure the change in voltage over the change in current when a current is drawn from the output. So we can use the voltage with the Ix load shut off as one data point, then use the voltage with our load current of Ix as the second data point to get the change in voltage over a change in current from 0 amps to Ix amps. Plugging in these 2 voltages and 2 currents, and canceling out terms, produces an output impedance, as expected, of RC in parallel with RO. So now we have our three terms here. While these equations are fairly accurate since all sources have some resistance and RO is always present, as I have warned before, being too accurate can detract from insight and intuition regarding a circuit. And so we need to simplify these equations based on some assumptions. First, we assume that the source resistance is very small and much less than RB prime. Second, we assume that RC is much less than RO. Third, we assume that the parallel combination of the two biasing resistors is much greater than R pi. This produces the more classic results. Gain becomes negative GM times RC, input impedance just reduces to R pi, and output impedance reduces to just RC. We'll continue today with using these assumptions, though we'll revisit them in future videos to see what happens when they break down. So expanding out GM and R pi to explicitly see the dependencies on IC and beta, let's think about the implications of this for a moment. Firstly, we notice that the gain of the circuit is negative. This is due to the direction the currents flow given the applied voltage. This is usually not an issue, as you can usually adjust your downstream circuitry to accept the inverted signal or invert the signal again using a similar transistor amplifier circuit if you really need the overall gain to be positive. Secondly, we see that we can very easily control the gain of this circuit just by changing the collector resistance. This makes it very easy to program the gain we need, though if you change the collector resistance to be too high, you will eventually push the transistor bias out of the forward active region. However, so long as you keep that in mind, you can very easily control the gain. Thirdly, the gain is also controlled by the bias current, and we can see that increasing the resistance and the current to increase the gain will increase the voltage drop across the RC resistor, which limits the amount of gain you can get out of the system by VCC. So higher VCCs generally allow you to have higher gains with this particular biasing circuit. Finally, the gain is inversely proportional to absolute temperature, so it will move around with temperature, which is not ideal, and for precision circuits, this effect needs to be managed and mitigated. Looking at the input impedance now, we see that increasing the collector current generally decreases the input impedance. So if we need the amplifier to have high input impedance, make sure not to set the collector current too high. And finally, the output impedance. Sort of opposite to the input impedance, if we need to have a lower output impedance, which is generally better for a voltage amplifier, in order to get the same gain, you have to decrease RC by the same fraction as you increase the collector current. So that produces a trade-off regarding collector current between input impedance and output impedance. Now that we've got our equations, let's demonstrate this circuit on a breadboard in the lab. Let's start by deciding upon a collector current and a desired gain. We'll start with a collector current of 1 milliamp and a gain of 10. A collector current of 1 milliamp translates to a transconductance, or GM, of 38.46 millisiemens. A Siemens is equal to an amp per volt, which is the unit for conductance. Using our gain equation and rearranging it to solve for RC, this produces a resistance of about 260 ohms. 260 ohms is a non-standard resistance, so let's set it to 330 ohms and settle for a gain of about 12.7 instead. In my circuit, I have a plus 12 volt rail, though it's more accurately around plus 11.8 volts. So I can put a significant amount of voltage across the emitter resistor. Recall that the more voltage dropped across the emitter resistor, the more reliably I can set the biasing current. So let's put 5 volts across it. This means to get a collector current of 1 milliamp, the emitter resistance needs to be set to 5K. Nearest standard value I have is 4.7K, so let's set the emitter voltage to 4.7 volts instead. So with VE set to 4.7 volts, VB needs to be set to 5.4 volts. Before we set the values for the biasing resistors, we need to have a better understanding of R pi and RS. RS is going to be around 50 ohms, since I'm going to just use my function generator, which has a 50 ohm output resistance. And the transistor we're using is a 2N3904, which at 1 milliamp collector current has a beta that ranges from 70 to 300 at room temperature, though the 300 number is taken from a more optimal collector current since the datasheet doesn't indicate a maximum value for the 1 milliamp collector current. This translates to an R pi of from about 1.82K to 7.8K. Ideally, we would want the combined parallel resistance of RB1 and RB2 to be over 10 times this value, so we can ignore it in our small signal model. However, due to practical reasons, I'm going to set a target for the parallel combination to be 50K or larger, and assume that beta doesn't actually get as high as 300. Now, since we're pushing RB1 and RB2 to large values compared with RPi, we're going to need to check to see how much this impacts the base voltage. So we see that the base current due to the beta and IC bias values varies from about 3.33 microamps to 14.3 microamps. Assuming a 50 kiloohm Thevenin equivalent resistance for the RB1-RB2 divider circuit, this translates to a base voltage decrease due to the base current of 166.5 millivolts to 715 millivolts. Given our 4.7K emitter resistance, and assuming all this voltage drops across that emitter resistance, and our VBE voltage stays at 0.7 volts, this translates to a change in the collector current of about 35.4 microamps to 152.1 microamps, or 3.54% to 15.21% of the collector current. This is a little too significant. The errors are piling up a bit, especially with the 0.7 volt assumption on base emitter voltage. As a result, I'll set the biasing resistors to a target above 6 volts, and put a potentiometer in series with RB1 to allow me to adjust the bias point slightly until the emitter voltage is 4.7 volts, ensuring that the emitter current is very close to 1 milliamp. So the resistance of RB1 is set to 100K with a 100K potentiometer in series with it, and RB2 is set to 122K by using a 100K resistor and a 22K resistor in series. Now the last thing we need to do is set the capacitances. I would like the capacitances to have effectively zero impedance at about 1 kHz. A good approximation for this is that they need to have less than 1/10 the impedance of the smallest resistance they interact with. For C-in, that would be the 50 ohm source resistance. The capacitance of a capacitor at 5 ohms and 1 kHz is about 31.83 microfarads. So I'm going to use a 100 microfarad aluminum electrolytic capacitor in parallel with a 10 microfarad ceramic capacitor to more than make this capacitance target. Second, we have Cout. If I were connecting this to another stage, I might try to set Cout's impedance based on the 330 ohm resistor. However, it's actually going to be the oscilloscope loading resistance, and if I set this output capacitance too high, it will take forever for changes in the bias point to allow it to settle. So I'm actually going to load the output with a 100K resistor, because that will have a negligible impact on the output resistance, and using this resistance divided by 10 at 1 kHz, I see that I need about 16 nanofarads. I'm going to set it to 10 microfarads, which is nearly 1,000 times what I need, but I don't think it will cause the settling to be that much of a problem. But note that the 10 microfarad cap here is a bit overkill. Finally, we have CE, which is a little bit more complicated. We haven't discussed this yet, but the impedance we need CE to be significantly less than is not RE as you might expect, but rather lowercase re, which is a small signal parameter equal to alpha over GM. We will discuss this small signal parameter in greater detail in later episodes when we go over the emitter-follower transistor circuit. Alpha, as you might recall from an earlier video, is equal to beta over beta plus 1, which is minimally 0.985 for our minimum beta of 70. This means that this resistance is at least about 25 ohms. So I need the emitter capacitor to be 2.5 ohms or less, which translates to a minimum capacitance of 63.7 microfarads. So I put another 100 microfarad electrolytic capacitor in parallel with a 10 microfarad ceramic capacitor. So now that we have our values set up, let's place our oscilloscope probes. We've got channel 1 on the output of the function generator and channel 2 on the output of our circuit. Note that since we're going to be taking our V-in measurement after the 50 ohm resistance, that the actual source resistance, Rs, of this circuit amplifier is 0 ohms, not 50 ohms, though this will have very little impact because 50 ohms was pretty small to begin with. I also want to point out that in order to demonstrate this circuit well, we have to use very low voltages and measure those voltages. Oscilloscopes in general don't do well with sub 10 millivolt signals. In particular, 10x probes introduce a lot of thermal noise into the system, as well as incorporating a factor of 10 reduction in the signal. Fortunately, 10x probes only become necessary at relatively high frequencies. So long as we keep our frequencies low enough, we should be okay to get rid of the 10x probe. We're running this circuit around the 1 kHz to 10 kHz range, and so I'm connecting these signals directly to the scope using effectively a 1x probe rather than a 10x probe. Additionally, I'm triggering the scope using its trigger input and a TTL output that my function generator outputs alongside the main signal. This produces an extremely reliable trigger, allowing me to use a combination of the oscilloscope's averaging function and its digital filtering to clean up the signal even more so that we can see it clearly. So we see that the input voltage on channel 1 here in yellow is around 4.64 millivolts, and channel 2 in blue is about 54.4 millivolts, a gain of about 11.72, which is close to our expected gain of about 12.7. Now let's see what happens when we increase the amplitude of the input. Here I'm changing the number of averages just to increase the speed at which the waveform updates. And because increasing the amplitude means that there's less noise that I have to reject with averaging. Here with the input voltage at about 14 millivolts peak to peak, we can see a little bit of an asymmetry in the output waveform. The top portion of the waveform seems to be wider than the bottom. Going to a higher voltage, with about 30 millivolts peak to peak, we can definitely see the asymmetry. This is a nonlinear effect which is caused by our small signal approximations breaking down. The small signal is not small enough. Continuing to increase the input voltage continues to make the nonlinearity worse, as we might expect. And as we keep going, we can finally see the top of the waveform flattening. This is because we've pushed the output signal high enough that the collector current is shutting off, because the input signal voltage is going so low that it's actually causing the transistor to turn off, and the output cannot go higher than its positive rail. And we see that increasing the input signal further causes the low portion of the output to go lower, but the tops of the waveform don't go any higher. You'll note that the maximum voltage output isn't very high with this particular circuit without getting very nonlinear. One way of increasing the output voltage range is by simply increasing the gain. To demonstrate higher gain, we're going to change the circuit a bit to facilitate viewing this higher gain circuit. Here I've changed the collector resistor to 3.3K to increase the gain by a factor of 10 to about 127. Additionally, I've removed the 100K resistor on the output and replaced the 10 microfarad Vout capacitor with a 100 nanofarad capacitor. This is because the 100K resistor will start to have some effect on the 3.3K resistor, and so it's better to just rely on the 1 megaohm of input resistance on the scope probe. Also, we've added a much more complicated input stage. We have the function generator going into a resistive divider, which will be tuned to apply a gain of 0.01, or an attenuation factor of 100, which then goes into a unity gain buffer provided by an LM324 op-amp. Although it is not shown, I have attached a 10K resistor to my negative 12-volt rail on the output of the LM324 to eliminate any crossover distortion. The purpose of this circuit is to have an input signal that my oscilloscope can actually measure well, which is then attenuated by a factor of 100 to make it much smaller before being input into the common emitter circuit. Were I to measure the attenuated signal directly with the scope, it would be virtually impossible to see. So channel 1 of the scope is put on the output of the function generator and channel 2 on the circuit output. So we just divide the signal on channel 1 by a factor of 100 to get the common emitter amplifier subcircuit's true input voltage. Channel 1 is showing 504 millivolts peak to peak, which means that Vin is about 5.04 millivolts peak to peak. And channel 2 is showing 568 millivolts peak to peak. This results in a small signal gain of about 112.7 volts per volt, which is pretty close to our target of 127 volts per volt. Right off the bat, we can see that the nonlinearity with this circuit is much lower for the same peak-to-peak output voltage. With the previous circuit, with the input voltage of around 30 millivolts and an output voltage of around 336 millivolts, we could clearly see nonlinearities. Here, with the output voltage at 568 millivolts, it appears to be much more linear. Now we increase the input amplitude to see how the output changes with this circuit. And at around 2 volts output voltage, we start to see some nonlinear behavior, which we saw at a much lower output voltage with the previous circuit. So this is again because this nonlinearity is caused by large input voltages, not large output voltages. And so larger gains mean that for a given peak-to-peak output voltage, there's a smaller peak-to-peak input voltage. And now, with a large enough amplitude, we can see flattening on the bottom side of the waveform, which is not what we saw with the previous circuit. This is because the collector voltage without any input voltage is biased to a much lower voltage in this circuit, about 11.8 minus 3.3 volts, so about 8.5 volts, rather than 11.8 minus 330 millivolts, or about 11.47 volts. So with an output peak-to-peak voltage of 6.48 volts, the transistor is drawing so much collector current at the bottom portion of the output that the output is actually getting so low that it's pushing the collector-emitter voltage close to zero, violating our requirement that the collector current be less than VCC minus 0.7 volts divided by the collector and emitter resistances in series. So the collector is unable to go any lower since the collector cannot go lower than the emitter voltage. That concludes this episode. In the next video, we will be introducing the common collector circuit, or emitter-follower circuit, going over its use cases and exploring the small signal equivalent circuit for it. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.